the thing that we saw that happened in WPA was a new style of attack. The old style of attack was to break WPA2 in pre-shared key mode, not enterprise mode. So if you're doing enterprise mode, especially with EAP TLS like you should be, it means you're comfortable with certificates, you got your own CA server. I don't know of any public attacks. If you're using pre-shared key mode, yes, there have always been public attacks, and that's used to be that you had to require a handshake of a device logging in. It's still easy. You can sniff from a quadcopter or drone. You can fly drones autonomously. You can attach a Raspberry Pi or other wireless sniffing device to a drone. You can sniff from 500 feet above. All you need is a handshake. So if my battery lasts for 30 minutes, I'm hovering over your house or office, I promise you a tablet, a phone, a light bulb, some IoT device is probably going to turn on and authenticate. So breaking WPA in the old days was kind of like phishing. You had to wait for somebody to authenticate. Now you could speed it up by doing some attacks and knocking people off. Sometimes that would be detected by intrusion detection sensors. Sometimes it would be detected just by the users because they would kind of know what was happening. But for the most part, if you're patient, you could capture that handshake. The new attack that just came out, they said you don't even have to wait for the handshake anymore. So they made an attack that already existed quite a bit easier. But that takes us back, like you even looked at WEP. WEP was garbage. It was wired equivalent privacy. I didn't trust the wire. So the fact that WEP was broken, big deal. We're still validating by MAC address. I'm still forcing them into an IPsec tunnel as soon as they attach or they can't talk to anything, including each other. So you can do secure wireless. There have always been ways to break it, but there's always kind of slick things we can do to make it work a little better. What we're talking about here is how you make it work better. If your home access point, maybe it's something that you're not real impressed with. Can you run OpenWRT on it? Not that they've had a bulletproof history of no flaws, but you can start to implement a lot of the better security features on your wireless. So just kind of stepping backwards, these are some newer standards that we talk about. The newest form of Internet Key Exchange, IKE version 2, it's like a protocol update. This is going to leverage EAP. WPA2, WPA3, when implemented properly, are going to be doing EAP. 802.1x does EAP. So this is something we want to know about, and it was basically the evolved version of PPP. Now to understand this at its most basic level, again, PPP had PAP and CHAP. PAP was clear text, CHAP was challenge handshake. So let's look at what that looks like. You got a client, you have a server. When the client wants to authenticate to the server is going to send a challenge. Just think of this as a random string of characters. What the client is going to do is take the challenge, which is a random string, take the password, and then take an algorithm that you run it through, typically a hashing algorithm. So the challenge crossed the wire, the password we had stored locally in a config, and what I output here is a digester hash. This is what's called the response. So the client tells the server, here's the digest that I just created. Well, because the server knows the password, and because the server is the one that actually created the challenge, they're going to do the exact same thing. They're going to create a digest. And this is common. We're going to see this again and again. When we're verifying digital signatures on mobile applications, when we're doing an SSL handshake with the web application, this is the same thing again and again and again. Somebody sends a challenge, somebody hashes it. What do? We match the hashes. And if the hashes match, the authentication is actually true. This is, in some cases with packets when we do this, it's called hash message authentication code. We're using a key, we're hashing the data. If somebody gets it, they can go, this data really came from my partner, and B, it wasn't altered in transit. So the idea of CHAP, and what we really want to take away from this, the idea of challenge response, is that the server side sends a challenge across the wire and a digest comes back. Some people will incorrectly say, okay, well my password was encrypted before it crossed the wire. Nope, this isn't encryption. Encryption gets decrypted. This is just being duplicated or recreated. I created a digest, they created a digest, only possible because we were both using the exact same inputs on our algorithm. Now, could this be broken? Sure. Anybody who has access to the wire, service providers, nation states, etc., they see a challenge go by, they see a response come back. All these protocols that we use are public. The length of the digest can show you what algorithm was being leveraged. So it's not terribly hard to reverse this. Now we can say the challenge plus what value is going to generate that response. And if you run it through an algorithm and you can determine what challenge would create the same response, this is where you can come up with the password. How are we doing? Is this a little bit slow? Right on track? I don't think I would have lost anybody yet. Just hoping that this is hopeful for some people that weren't real familiar. Something we want to be super solid on, because as you start looking at some of the EAP types, you're going to see like EAP MD5, they can do attacks against. EAP TLS, not really. Doing good, on track. Okay, cool. So that's kind of the same thing here. They're like, well, it's NTLM authentication. I wouldn't even think about it that hard. Whether it's NTLM or Kerberos, you got a challenge and response. If we can capture the challenge and the response, we can look at port numbers, we can determine what protocol is in use, you can load it into utility, and you can attack the password. So what some people will do, not to get too far ahead in the story, but we did already talk about EAP, Extensible Authentication Protocol. The weakest version of this that I typically hear about or see people complaining about is EAP MD5. Another version that exists is called PEAP. Without saying that it's good or bad, I like the idea about it. They say we're going to do protected EAP. So whenever you want to authenticate, what you do is you talk to the server from the client, and the server is going to give you his digital certificate. Digital certificate, we'll talk about this more at the end of the class. We got a crypto section. But you basically have a public key, and we're just trying to tie identity information to it. So a fully qualified domain name, an organization, a city, a state. For anyone to believe it, it has to come from a certificate authority, which is a trusted third party. And then, of course, the certificate itself has details, a serial number, an expiration date, some diagnostic and administrative details in there as well. Well, if the server gives you his digital certificate, and we've all seen this in a web page before, as soon as you get it, your crypto stack on your computer looks at this X.509 version 3 digital cert, and the certificate itself has a digest. And this digest happened to be encrypted. And when we encrypt digests, we call them digital signatures. The person who encrypted this digest was actually the CA server with the CA server's private key. So anybody who can decrypt this, and remember we were just talking about verifying digest with CHAP, if somebody sends me the digital certificate, I can hash this digest and put it to the side. I can take this digital signature, use the CA server's public key to decrypt it, and guess what? It's a hash. If these hashes match, I know that the certificate's valid. Woohoo! What's that do for me? It says I can now use this public key to encrypt data. This is asymmetric encryption. Anytime I take data and I encrypt it with the other side's public key. Who has the public key? Everybody in the world. Go to www.microsoft.com, view the certificate. That's the public key. It is useless for decrypting data that's set up in this way. See, because everybody has the public key, anyone that was to take data, encrypt it with this public key, is going to create ciphertext. That ciphertext can only be decrypted by the private key. Well, the only person that has the private key, in this case, is the server. So a digital certificate is just a way to get your public key to somebody else. Does this have performance implications? Of course. It all does. But when we look at our servers, when we look at load balancers, this is something that they're anticipating. Sometimes there's even dedicated chips for crypto functions. So let's just look at it just from a web browser, because this is something you want to be pretty comfortable with. One more time. There we go. you hear this stuff, but sometimes it's not always really easy to visualize. So like here I am at start page, and it's over HTTPS. I have a green lock. That's exciting. Just mousing over the green lock, it said that this was verified by the Komodo Certificate Authority. So here I am going to start page. Start page gave me that X.509 digital certificate. What does it really contain? The public key for start page. How do I know it's public key start page? Because it has their identity information in there. Why can I trust it? Because somebody created a hash of this and they encrypted the hash. That's called a digital signature. Who the heck did this? The company called Komodo. Okay, so if Komodo is someone that I trust, your devices, your operating systems have got trusted third parties already in them. So I've got a Komodo public key. It means I can decrypt anything that they encrypt with their private, which isn't for privacy, it's for authenticity. I know that this public key really goes with this identity. In my case, start page. Why? Because a hashed version of that information was encrypted by Komodo, and I could use their public key to verify that. Is that pretty easy? This is certainly not the whole story, but it's just kind of understanding. Okay, said no. Good answer. If we were all in live class, I'd go, that was easy, right? And I'd look across the room and I'd know in a second. How is the hash made? Well, let's go and just look at it for a second. When we come over here and we look at the certificate, there's all these details, there's all these aspects to talk about, but what makes all of it work, what makes any of this secure, is what you see right here. It says modulus 2048 bits, and if we go one block higher, we see RSA. That sounds familiar, right? RSA encryption, public keys, private keys, government conspiracies, all we see is. How do I trust Komodo? Maybe you shouldn't. That's my big question. You know, you have an iPhone, they picked like 100 CA servers and they go, you're just gonna trust all these guys. That's how the world works. And you go, I didn't want to trust those guys. So I go into like my Cubes box and I pull out every single CA server that I don't need. Yes, I need to get to Windows Update maybe. You know, not on a Cubes box. Yes, I need to get to Symmetric's updates, Cisco's updates. Who did they use? And do I really need to browse from the server? No. Do I need to go to 100 other websites? No. Do I need to go to China? I don't. So I rip out all the CA servers I don't need. So if any of them are ever compromised, it's not going to come back and hit me. CA servers have been compromised in the past. But kind of going back to the whole point of this, and I guess we've got a whole crypto chapter that happens later, but effectively there's two types of crypto. There's symmetric and asymmetric. Example of symmetric is AES, asymmetric is RSA. Symmetric means you've got the same key on both sides. So we see strengths of things like 128. RSA says we're going to have a public key and a private key. You're like, what? And it's like, well, we're going to have two keys. This blew a lot of people's minds because for over 5,000 years, we've been doing symmetric encryption. That was the only way to do it. And the flaw we've always had is like, well, crap, how do you get the key securely to the other side? You would not believe the things that they've tried over the years. Crazy stuff. I won't go there right now. But if you want, there's a great college course on espionage. It's available through Audible for like $11. One of the best stories in history. They've had to do a lot of crazy stuff to get keys from point A to point B. Then in the 1970s, the guys at RSA, Rivish, Shavir, and Adelman said, we've got this different crypto system where you create two keys, one that's shared with the world, one that's kept private, and whatever gets encrypted with the private can only be decrypted by the public. Whatever gets encrypted by the public can only be decrypted by the private. Really kind of weird. So they said, look, this is going to change the world. The Brits, of course, GCHQ, about the same time goes, well, you didn't invent that. You were just the first ones to talk about it publicly. They said they'd been doing it already. But what RSA or asymmetric encryption really does for us is it solves the problem of how do I get a key to the other side. Now, it's not coming without a penalty. In order to do that, because we've got one key that's exposed to the entire world, and we've got another key that's mathematically related to it, you can do brute force attacks against this. So the key size you'll see is like 2048-bit. And we're like, wait, I understand binary. If 129 bits is twice as strong as 128, I can't wait to use 2048-bit. And it's like, well, it doesn't really work like that. If you were trying to find something equal to 128, you'd be looking at roughly 3000-bit RSA. Why is that? Because the attacks are different. Because part of the key space is exposed, we have to use much, much bigger keys. But that's okay. When we look at AES, it's very fast. It's very simple to do. We look at RSA, it's slow, it's heavy, it's complex. And that's why we never ever use it for bulk data encryption. So we took a side road to Crypto Town, but this is all good stuff that we had to cover. I'm going to show you a little bit about asymmetric crypto. A good place that gets people confused is SSH. If you were ever a client connecting to a server, right, TCP 22, trying to get to open SSH, when I get there, three-way handshake, of course, there's going to be SSH version negotiation, but the server is going to send you the public key. So people see this and they go, aha, SSH uses RSA. I'm using asymmetric encryption to be more secure. And I hear that and I go, well, not really. Here's what's actually happening. And has everybody seen a public key come across for SSH before? I'll assume yes. If anybody hasn't, say no, and I can step it back a bit. But just taking for granted, everybody's done an SSH session. What happened? A key pops up. It says, do you accept this? And we're like, yeah, whatever. Yes, and save. We just smashed the yes and save button that Putty threw at us. Well, what did we just really experience, right? You always agree. But what's happening there is this server is authenticating to you. It goes, hey, remember that day we hung out? You basically booted me. I was born. You made an open SSH key. It was really exciting. You saved it, right? See, what you're supposed to do over here is the admin. When you generate your RSA keys, you take the public key and you save it somewhere. It's not real sensitive, but you just save it maybe in a local document in your documents directory. Router1 RSA.txt. What's in there? The public key. Now, the first time you log into Router1, when it says, hey, here's my key, just verify it. Look, did it match? Sure, cool. Yes, and save. What happens next? We run an algorithm called Diffie-Hellman. This is some crazy math that's going to get the same key on both sides. So imagine that our encryption key is encryption key 1, 2, 3. Diffie-Hellman just did it for us. Now that we've got the same key in both places, we'll move over to using symmetric encryption. In the old days, it was triple DES. Now it tends to always be AES.